Okay, there was another cut here, but let me just finish off by saying this, talking about how you can orient this ester group here is when you see the peak integrating for this set of hydrogen that's next to the single bonded oxygen of the ester, when you see the peak for that being super high at like 4 ppm, the highest, then you know that those hydrogen must be next to this oxygen right here. Okay, the ppm, the chemical shift value for these hydrogen is actually about half of the chemical shift value for this one. So this is lower than this one. So when you see the peak integrating for these hydrogen, for these hydrogen being super high around like 4 ppm, then you know that these hydrogen must be next to the oxygen that's singly bonded as part of the ester. Okay, all right. Okay, so I hope I did not bore you guys yet with my rambling and long explanation, but I would say that we have reached the most important part of our practice exam, is this problem. Okay, so first, which one is your electrophile? How you can tell. Okay, so, right. I have here a reaction that I want you guys to do, okay? And I said electrophile is because I want you guys to do a nucleophile electrophile reaction, okay? So let's start by identifying the electrophile. Okay, so how do you identify electrophile? Is anything with positive charges, partial positive charges, or missing octet. Okay, so we have here on the right an outstanding positive charge on a sulfur. Sulfur, being fairly electronegative, has to bear a positive charge, so that makes it pretty unhappy. So that would be our electrophile because of the red flag positive charge. Okay, but which part of the molecule actually holds the positive charge? Now this is where I want you guys to pay close attention to. This is very important. Hen hen, wink wink. This is a very important indeed. Let's identify all of the atoms, okay, that hold the actual partial positive in this molecule. That is our electrophile, right? Okay, I'm gonna switch to blue. Okay, so sulfur again has to bear the positive charge. Okay, so it is very hungry for its electron because of the price that it has to pay for bearing that positive charge. Okay, so it is gonna hog all of the electrons in these three bonds. Okay, so I have like the polarity diagram, I guess, drawn here. So all of the polarity points to sulfur, okay? Meaning the electrons living in these bonds are being hogged very close to sulfur, okay? And so the atoms that hold the partial positive are the hydrogens and this carbon, okay? The carbon, the hydrogen, have the actual partial positive, and so these three atoms, the three partial positive atoms, are valid. They're all valid targets for a nucleophile to attack, okay? You have to understand this, okay? This is very important. Wink, wink. Okay, so this is pretty similar to what you guys have been seeing before, like in the hydronium ion, okay? So our good old H3O plus, okay? Now oxygen, again, like the sulfur, very electronegative, has to bear the positive charge. So it seeks out the electrons living in these bonds right here and pull it close to itself as much as possible, leaving these three hydrogens very partial positive. That is why any one of these hydrogens can be readily attacked by a nucleophile, or in this case, a base, right? Which makes them very acidic, okay? Less than 0 pKa, if you remember, right? And that will be similar to our sulfur, okay? Our hydrogens will be very, very acidic, okay? It is extremely acidic. Possibly even less in pKa than this hydronium ion hydrogen, okay? So for our nucleophile electrophile reaction, it is actually specifically an acid-base problem. So a proton transfer reaction, okay? Now I say, okay, so now we have identified the actual electrophilic atom in our electrophilic molecule, that is the hydrogens and the carbons, and hydrogens are acidic, so we are gonna attack the hydrogens, okay? So now let's look at our nucleophile. So nucleophile, there could be multiple nucleophilic sites or basic sites. You have to look out for that, and a way to look out for multiple nucleophilic sites is through resonance structure, moving the negative charge around to different atoms, and in turn those atoms can be the nucleophilic sites. So here we have our first atom that holds the negative charge that is on the nitrogen, and then you can resonate it to the right and up to this carbon atom right here. That will be our second nucleophilic site, and then you can move it down to that oxygen, and that will be our third nucleophilic site. So we have three nucleophilic sites, three atoms, the nitrogen, carbon, and oxygen down here, okay? So those would be your nucleophilic sites to use. I get it that there are also, you can also identify nucleophilic sites with partial negatives or just like electronegative atom, and we have tons of it in this molecule. We have sulfur, we have another nitrogen, we have a third nitrogen, but those are not nucleophilic sites. You have to keep in mind that when you're doing these reactions, this is also important, you have to keep in mind when you're doing any reactions in organic chemistry is to form products that are as stable as possible, okay? So we know that it's going to be a proton transfer reaction, so you're using these nucleophilic sites as basis to attack the hydrogen right here, okay? So you're going to be putting hydrogens on this nitrogen right here, okay? Neutralizing that negative charge right here, which is great. We get a neutral molecule. You are neutralizing this carbon negative charge on this carbon right here, great. And also on this oxygen atom as well, great. But if you use the sulfur to attack the hydrogen, you'll get a positive charge on the sulfur, and you still have not done anything to neutralize the first burden. Does that make sense? The first burden has not been taken care of, and you give it another, and you just give it more work. Okay, so you will end up with two charges on one molecule, and that is super unstable, and your goal is to form the most stable product as possible. So the only nucleophilic sites that would lead you to the stable products would be through these three nucleophilic sites, because those three do not give you more charges. They lead you to a neutral molecule. Okay, so because this resonance tells us of these three nucleophilic sites, use those to attack the hydrogen, which is super acidic in this case. Okay, okay, last reaction problem, which actually has a built-in of two reactions. Okay, all right. So for the first part of this reaction is I have you guys draw product A as well as the arrow pushing mechanism leading to it, and I told you guys that it's a proton transfer reaction. Great. Let me zoom in a little bit more. Okay. And I also asked you where the equilibrium will lie. Okay, so what's the first step? I told you guys it's a proton transfer reaction. So okay, first, which one is your base? Most likely this nitrogen, because K is potassium. It is a metal, so we don't care about it. It's spectator ion. It'll appear here in this reactant site, and it'll appear again in this product site. So if you're drawing the net product, they would just cancel each other out. So just cancel it out. So you'll end up with an N minus. Okay, right? The minus is a giveaway that it is a strong base. So this molecule must be your acid. Great. So which one is your acidic hydrogen? Now, first things first, there's a CN here. This condensed formula is also infamous for giving people trouble in the past, so we're gonna expand it. So I have expanded it right here. It is our good old nitrile group, C triple bond N. Okay, right? So this hydrogen would be the most acidic option within this molecule. Now again, we have hydrogens here, but as I warn you, do not ever pull off hydrogen next to an oxygen or a sulfur, or just like a single bonded nitrogen, because the electron clouds would, electron density around this area would be really great, and all they want to do is just get away from each other, because like charges do not like being too close to one another. Yeah, and this one is the same thing because of this. Okay, so this is the only one. Not only because this is the only one, because, well, okay, yeah, this is the only one. Not only because these two are not an option, is because this is able to resonate up with this nitrogen, okay, after you pull off the hydrogen. So I just have, this will be the arrow pushing mechanism for it. I have the lone pairs on the nitrogen, go attack the hydrogen, and have the electrons living in the bond go up as a lone pair, like here. And then it is resonance stabilized. Okay, it can resonate up to the nitrogen. Great. So, right, predict where the equilibrium will lie. Now, Ario does not work here, okay? Let's take a look. If we apply Ario, we would say that this is more stable than this, right? Because the negative charge is on a nitrogen, whereas the negative charge over here is on a carbon. So atom effect would say that negative charge on a more electronegative atom, in this case nitrogen, is better than carbon. Hence the nitrogen with the negative charge would be a more stable base. And so equilibrium always lie towards the more stable side, so it would go towards the left. But pKa says otherwise. Equilibrium will always lie to the side with the more stable species, right? And that also applies to the acid as well. And in the case of acid, we would need a higher pKa, okay? So the pKa for this hydrogen, you guys don't really know this yet, but the pKa is actually around 25. The hydrogen that's next to a nitrile group is 25. Now you guys don't know this yet, but this is what you're gonna have to do in OChem, is to find similarities, okay? I think you guys were asked to memorize the pKa for like the hydrogen next to like a carbonyl group. Now this acts similarly as a carbonyl group. Like if you do resonance, it almost looks the same. So yeah, it will make sense that the